Alright, this is exam 1 for physics 202 in spring 2011. The first one that says this figure shows two charges and their electric field lines. If the charge on the left has a magnitude of 6 microcoulombs, what is the sign and magnitude of the right charge? So this one is 6 microcoulombs, and because the field lines are ending at this charge, it's negative 6. If we count these field lines, there are 6 field lines over here. There are 12 field lines over here, so this one has twice the charge, which is positive 12 microcoulombs. That is A. Which of these is not a valid charge? Alright, this is an electron. This is 5 protons. 5 times 1.6 times 10 to the minus 19 gives you that value. This is a whole bunch of electrons. However, this is like, I don't know, 4 point something protons. So A is not a valid charge. You find that by saying 7.0 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19, and it's not an integer, so it's not an even number, so it's not a valid charge. Consider this configuration of charges. Which vector best represents the net force acting on the rightmost charge? Alright, so this charge, the force is acting on it. First, the force acting on it from this charge is in this direction, and then the force due to this charge is opposing, and it's a little less than half that of this other force, so it's considerably smaller. It's smaller because this charge is smaller than the minus 4q, and this charge is also further away, so the force is less by a factor of 2, by more than a factor of 2 rather. And so the sum of these two force vectors gives me E, so number 3 is E. In this figure, two charges are separated by a distance d. The point A is equal distance between the two charges. Point B is distance d over 2. So points A and B are the same distance from the negative 4q charge. What is the where is the electric field of the magnets have its greatest magnitude? Well, let's just draw our force field vectors. At point A, the electric field due to the plus 2q charge is in this direction, and the minus 4q charge is twice that value, and in this direction. Over here, the electric field due to the 2q charge is small, even smaller than we drew it here, because it's further away, and the minus 4q is in this direction, and it has the same magnitude as it did over here. So the sum of these two, or the greatest electric field, is at point A. Which best describes the work required to move the charge along the dotted line in the figure? Well, this is an equal potential line. Work is Q delta V. The potential doesn't change, so the work is 0. This figure shows how particles A and B respond to one another. Let's see, A and B are like charges. That's not true because they attract to one another. They're actually opposite charges. A and C are opposite charges. That's not true. They're like charges. And now let's see, B and C are like charges, or B and C are opposite charges. Well, let's just say, what if A is positive? That means that B is negative. A is positive, so C is also positive. So B and C are opposite charges. That's D. Number 6 is D. Proton and electron are a constant electric field as shown. You release an electron and proton at a point equidistant between the two plates. Which particle has more kinetic energy when they strike the plates? Well, potential energy, or the work, is Q delta V. Right, they have the same change in potential, right, because they're moving through the same electric field. And they also have the same charge because they're a proton and an electron, so they have the same magnitude of charge, so they have the same kinetic energy then. In this figure, an electron sits between two charged plates. The electron moves to the right in response to the electric field. What is the direction of the electric field in between the plates? In order for a charge to move in this direction, a negative charge, the electric field has to be opposite that direction, which is to the left, that is D. In which of the following diagrams is potential on the x-axis equal to 0? Alright, on this one, there are all negative charges, so the potential can't cancel out at all. Here, at this point, this distance is smaller than this distance, and likewise these distances are dissimilar, so those potentials don't cancel out at any point along the x-axis, and that's also true for this one, that these distances are different, so the potentials don't cancel out. So the answer for number 9 is D, that none of those have the potential on the x-axis equal to 0. This figure shows a positive charge with concentric circles surrounding it. At what point is the potential its greatest value? Well, V is kq over r. So where r is smallest is where your potential is biggest. That's at point C and D. And they're along an equal potential line, so they have the same potential. These 6 charges at the corner of an equilateral hexagon, what pair of statements best describes the electric field and potential at the point in the center of the hexagon? Well, for the electric potential, you have to have equal numbers of positive and negative charges. So you have negative Q, negative Q, negative Q, positive Q, positive Q, positive Q, 3 each. So V is equal to 0. And now let's draw the electric field vectors for each individual charge. So I'm going to start with this charge. The electric field due to that charge is in this direction. The one due to this charge is also in that direction. The electric field due to this charge is in this direction, and the electric field due to this charge is in that direction. The electric field due to that charge is to the right, and likewise this charge is to the right. So the net electric field is not equal to 0. It's actually a negative electric field towards the left. So E is not equal to 0, V equal to 0, V is equal to 0, so that is B. Parallel plate capacitor initially has a potential difference of 200 volts and then is disconnected from the charging battery. If the plate area is now doubled, what is the new value of the voltage? Well, Q is equal to CV. If we increase the plate area, that doubles the capacitance. If the charge remains constant, then we have to have the potential. So it was 200, now it's going to be 100 volts. That's number 12 is A. Consider this circuit. All 3 capacitors are identical. What is the voltage across C1? Alright, well, these are in parallel, so combined, these 2 capacitors have 12 volts, which is these 2 capacitors have 12 volts, which is the potential supplied by the battery. And since the 2 capacitors are identical, they split that voltage, so they each get 6 volts. So the answer is C. Consider this circuit. All 3 capacitors are identical. What happens to the equivalent capacitance if one of the capacitors is removed? Right, the equivalent capacitance is actually going to increase. That's C. Can show you, let's just sort of put some numbers in. Let's say that they're all 4 microfarads. 4, 4, and 4. If I have 3 capacitors, that's 1 over 1/4 plus 1/4 plus 1/4, 1/4. That's equal to 4/3. Alright. If I only have 2 capacitors, that's 1 over 1/4 plus 1/4. That's 1 over 1/2, which is 2. So when I remove a capacitor, it actually decreases the equivalent capacitor. Or excuse me, when I remove a capacitor, it increases the equivalent capacitor. We'll see this again when we're dealing with the resistors in parallel. That if you remove a resistor, it increases, and vice versa. That is, if you add a resistor, it decreases the equivalent. What is the purpose of the dielectric and a capacitor? To prevent the plates from touching. Let's just look at the others. To increase the potential between the plates of the capacitor. Okay, that might occur, but that's not the purpose of it. To allow for the flow of charges, that doesn't occur, and there is no real purpose. The primary purpose is to prevent the plates of the capacitor from touching, so that you can wind up these capacitors into easy-to-use components. Alright, what is the electric field in vector notation at the point 2i minus 3j if the electric potential is given by this function? Well, first we just want to calculate the x and y components. Alright, and we'll calculate the electric field. Our x position is 2, our y position is minus 3. Ex is equal to minus del v del x, the partial derivative of v with respect to x. That is negative 2y cubed minus 2 plus 8xy. Plugging in my numbers, let's see, I get negative 2 times negative 3 cubed minus 2 minus 8 times 2 times negative 3. Just putting in those x and y coordinates, and this gives me positive 104, and this is in the I direction. Now EY is minus del V del Y. That's negative. Some of you left the negative signs off. I think I just counted maybe a point off for that, or maybe a half a point even. 6xy squared plus 4x squared. That's equal to negative 6 times 2 times negative 3 squared plus 4 times 2 squared. Putting those numbers in, I get negative 124J. So that's my electric field, is 104I minus 124J. That's in newtons per coulomb or volts per meter, whatever you choose. Alright, now in part B you're supposed to find the displacement in vector notation after a certain amount of time. And you're also supposed to assume that the electric field remains constant as the electron moves. So it's actually, the problem is actually quite a bit more complicated than this, because when you move out of that position, that is this position of x equals 2, y equals minus 3, the potential changes, and so the electric field also changes. So it's actually a fairly complex differential equation to figure out what is the position after this amount of time. But we said we're going to lock the electric field into this value and just figure out, in a simple way, what is the displacement. So we know that F is equal to QE, and also from Newton's second law that QE is equal to MA. My displacement I'm going to find from X is equal to 1/2 AT squared. And we assume here that the V naught is 0. Because the electron is placed there, that you take this electron, you put it in a certain position, so its initial velocity is 0. So we want to calculate its x position, and then it's also its y position, 1/2 AY t squared. So in order to do that, we first need to find out what is A, x, which is going to be Q EX over M, QEX over M. And so that's equal to minus 1.6 times 10 to the minus 19 over times 104 times 9.11 times 10 to the minus 31 kilograms. That's equal to minus 1.8 times 10 to the 13. Go ahead and find out what is AY as well. That's QEY over M. And that gives me a value of the AY, the acceleration in the y direction, is 2.18 times 10 to the 13 meters per second squared. And then we solve our x and our y values. So x is 1/2 AXT squared, where t is this time, 1 times 10 to the minus 5th seconds. And if we plug in AX and t, we find that x is equal to minus 913 meters. And then if we do a similar thing for y, it's 1090 meters. Alright, so we could express our displacement as minus 913I plus 1090J. That's in meters. Let's see, the point distributions here, in case you're wondering about how I graded. I gave 8 points for this part. For the accelerations, I gave 6 points, and for the displacements, 6 points as well. Alright, in this figure, a 20-volt battery is connected across capacitors of capacitance C1 equals 4 micro... Or excuse me, I'm sorry. You weren't supposed to... I said in class not to worry about this and just go with the numbers. This was from a different problem. Okay, but the circuit is different from that problem. So first, we just want to redraw this circuit so we can get a better feel for what it's like. So we have this 6 microfarad capacitor come up. At this point, you have a junction. You can either go to the 4 or the 1. There's the 4 microfarad capacitor and the 1 microfarad capacitor. And then once you get past the 4, you have another choice. You can go through either the 2 or the 2. So you have the 2 and the 2. Those two junctions come back together. These two come back together. And then they meet up back up with the 1 microfarad capacitor. So that circuit looks like that. This is C1. This is C2. C3, and then C4 and 5. Alright, the first thing you want to do is find the equivalent capacitance of C4 and 5. That's 1 over 1 over 2 plus 1 over 2. Or excuse me, no, I'm sorry. That's just equal to 2 plus 2, which is equal to 4. And then combine that with C2, which is going to be 1 over 1 over 4 plus 1 over 4, which is equal to 2 microfarads. So I can redraw the circuit again. There's my 6 microfarad. And then I have a 1, and now my C245, this is C245, has a value of, what did I say, is 2 microfarads. So this is 2 microfarads, this is C3, this is C1. And then combine those two, I'm left with a 6 and a 3 in series. This is C1, this is C2, 3, 4, 5. And then combine those. 1 over 1 over 6 plus 1 over 3 is equal to 2 microfarads. So that's my equivalent capacitance, 2 microfarads, which by the way was worth 4 points. What is the charge? Alright, this is just CV, so 2 microfarads times 12 volts. 2 times 12 is 24 microcoulombs. And let's see, I want to know what is V1. Let's see, V1 is this capacitor, alright, which is the same as this capacitor. Alright, I already know the charge on that one is 24 microcoulombs, and so V just is equal to Q equivalent then over C1, which is 24 divided by 6, which is 4 volts. And then V2, this was a typo but I fixed it on your test, this should say V2. That is the potential across this capacitor, which is, gosh, where is that? C2, which is this capacitor. Alright, now let's see, this has 12 volts, so these, we said that this one has 4 volts, and so this one must have 8 volts. Alright, if that one has 8 volts, this one has 8 volts, and this one has 8 volts. That's the C245. If this has 8 volts, these two capacitors, that is C2 and C45, if I replace this, it looks like something like this, which is 2 4 microfarad capacitors. So they're both sharing this 8 volts. So it's 8 volts divided by 2, which is 4 volts. Q2 is C2V2. C2 is 4, so that's 4 times 4 is 16 microcoulombs. Alright, V3 is the potential across this capacitor, C3, but we've already said here that it's 8 volts. So it's the same, well, we find it out because we say 12 minus 4 is equal to 8 volts. And then V4, if I can find it, let's see, we already said that the potential across this capacitor is 4 volts, and so these two capacitors, because they're in parallel, share that same potential, so that's 4 volts as well. Q4 is C4V4, which is 4 volts times 2 microfarads, which is 8 microcoulombs, and then V5, since it's in parallel with C4, it has the same, which is 4 volts. Now all of these were worth 2 points each, and generally I gave partial credit. So like for example, if you got this number wrong, but then for this one you said it was equal to CV, even though you're using the wrong number for V, I still gave you credit for it because you're calculating Q correctly. Similarly, if you got this number wrong, but then you put the same wrong number for this value, then I gave you credit for one of them, for usually I, because you recognize that it was the same as G. Alright, this figure shows 3 charges. Positions for each charge are given. What is the magnitude and direction of the net force acting on particle Q2 due to particles Q2 and Q3? This part was worth 10 points, and this part was worth 5 points. Almost, I don't think anybody got part B. So I think everybody lost about 4 points on that part. I'm pretty sure nobody got it. Now, but part A, many of you did get. So the first thing we want to do is draw our force vectors. force vector on particle 1. I want to know the force on particle 1. This is the force on 1 due to 2. And then this is the force on 1 due to 3. First, I just want to calculate the magnitudes of those forces. F12 is K Q1 Q2 over R squared. K is 9 times 10 to the 9th. Let me just put in the numbers here first. 9 times 10 to the 9th. 2 times 10 to the minus 6 coulombs. 4 times 10 to the minus 6 coulombs divided by R squared. That's this distance, which is 3 squared. This gives me a value of 0.008 newtons. And then in a similar way I can calculate F13. I'm not going to put in the numbers here, but we're looking at 2 times 10 to the minus 6 for Q, 3 times 10 to the minus 6 for Q, and then this distance, which is R, this is a 3, 4, 5 triangle, so this is 5 meters. If you put in those numbers, you get 0.00216 newtons. Now, I need to resolve this F13 into its x and y components. So I need to figure out what is this angle theta. That angle theta is the inverse tangent of 3 over 4, which is 36.9 degrees. Alright, and then I calculate the x and y components. F13 cosine theta, that's your x component of that force, and that's equal to 0.0021. Cosine of 36.9, which is equal to 0.00173 newtons, and then similarly the y component is times the sine of the angle, and that's equal to 0.0013. So those are my x and y components. If I draw these vectors now on a coordinate system, I have 0.008 in this direction, 0.00173, and then I also have 0.0013. 0.008 is F12, and then the other two numbers are the x and y components of this vector. Now if I subtract these two numbers, I get my two vectors, and my x and y components of the resultant force is 0.0067. That's 0.008 minus 0.0013. And then in the other direction is 0.00173. Now to find the magnitude of F, the net force is just the square root of the sum of the squares, 0.0067 squared plus 0.00173 squared. And that gives me 0.0069 newtons. Our resultant vector is in this direction. We'll say this is our angle phi, so this is part of the answer. And then the angle phi is the inverse tangent of opposite over adjacent, which is 0.0067, 0.00173, which is equal to 75.5 degrees. That's the second part of the answer, above the positive x-axis, but I think kind of off you didn't put that. Now, that was part A. That was worth 10 points. Part B, you're supposed to find the coordinates for a fourth charge placed such that the net force on Q1 is 0. So I want to place a fourth charge that will balance out these forces. So I want to place a fourth charge such that the force, F14, is in that direction. So I'm going to have to place this charge up here. This is going to be Q4. It has a value of +3, so that's why you have to place it up there. I already know that this angle right here is 75.5 degrees, because it's going to provide an equilibrant vector, that it equilibrates the force vector. So I just need to find out what is r, this distance. Alright, F14 is K Q1 Q4 over r squared. So r then is the square root of 9 times 10 to the 9th times Q1, which is 2 times 10 to the minus 6, Q4, 4 times 10 to the minus 6, over F14. F14 is going to have to equal the magnitude of this force, so 0.0069. Alright, in order to equilibrate it. So that gives me 2.8 meters. And then I want to find out what are the x and y components of that distance. So I want to know what is this distance, and then what is this distance. So x is r cosine of phi, which is 2.8. Cosine is 75.5, which is 0.7 meters. And then y is r sine of phi, 2.8 sine of 75.5, 2.7 meters. And then you just add them to these values. So my x value is added to 0. So the x coordinate is 0.7 meters. That's the x coordinate right here, this distance, x. And then my y coordinate is this total distance. So y is equal to 3 plus 2.7 is equal to 5.7 meters. Pretty sure nobody got this at all. Okay, this question was probably a little longer than it should have been, which is why I had it. So I justified this curve on this test. And okay, consider this configuration of charges. What is the potential at point P and how much work is required? So I want to know the potential. It's just, V is equal to the sum of KQ over R. So that is 9 times 10 to the 9th. Starting here and going counterclockwise, we have -5 times 10 to the minus 6 coulombs divided by 4 meters plus 6 times 10 to the minus 6 divided by this distance is 5 meters plus -3 times 10 to the minus 6 divided by 3 meters, and that gives you a value of minus 9450 volts. And then to move a 2 microcoulomb charge into the point P requires this amount of work. Work is equal to Q delta V. See, this is point A, part B. Q delta V is 2 times 10 to the minus 6 coulombs times negative 9450 volts. So it requires negative 0.019 joules of work. Those are the answers. Let's see, this was worth 6 points, and this was worth 4 points. But many of you, tried to calculate the potential energy required to assemble all the charges, and that just wasn't really what I was asking. So I was really just looking for the potential for part A, and then the work to bring in this fourth charge. Okay, capacitor. This was a pretty simple problem. Most of you got it. The area is 0.4 square meters. The distance between the plates is 1 times 10 to the minus 6 meters. The dielectric constant is 1.5. I want to know what is the capacitance. The capacitance is kappa epsilon naught A over D. That's 1.5. 8.85 times 10 to the minus 12. That's epsilon naught, the permeativity of free space. 0.4 over 1 times 10 to the minus 6, which gives me 5.31 times 10 to the minus 6 farads, or 5.31 microfarads. Many of you didn't put in this value. Like you said that this was equal to 1.5, but that's not really true at all. That's the permeativity of free space. It's a constant. It's on your equation sheet. I think maybe you just hadn't had enough practice working these types of problems. But I think maybe only one person actually put that value in. I generally only counted off 1 point if you did that. Another fairly common mistake, at least 2 of you did it, is that you put in for the area twice 0.4, but for the capacitor you only consider the area of a single plate, not both plates. So it was just a misunderstanding. Here are the answers to the multiple choice.